Thank you for coming to my talk, Unguarding Microsoft Credential Guard. So a little bit about myself. My name is Ceri. I'm from Wales in the United Kingdom. Us Welsh do tend to speak fast, so apologies in advance if you're struggling to keep up. So my background is in software development. I was there for 18 years, sort of in the DRM and security solutions space. And then back in 2019, I transitioned to cyber. And I'm currently a principal security consultant at NetSpy. So my role at NetSpy is split sort of 50-50. So half of that is R&D, and then the other half is on sort of red team operations. But I'm not particularly the primary operator in any of those engagements. I usually get pulled in to sort of help out on any obscure sort of software solutions that might be running within that particular client's environment. So I spoke at DEF CON a couple of times and various other conferences around the world. And quite often you might see me on the Bloodhound Slack HQ, helping out in some cases and leeching off others in other cases. So I'm an author and maintainer of several open source tools as well, predominantly in the sort of offensive side, but there are a couple of defensive-based tools on my GitHub as well. So what are we going to cover today? I'm going to give you a quick introduction, more of a high-level overview of what and how Credential Guard works. And then the first half, I thought I'd go over actual analysis and debugging for secure kernel, the hypervisor, and so on. And that will be targeted for people who are sort of interested in this type of work. And then after that, we'll go on to sort of secure kernel keys and how they tie in with Credential Guard secrets. And then we'll go into Kerberos specifics. So sort of how exactly Kerberos keys are protected through Credential Guard. And then we got some Rubeus goodies that have been included as part of this research, which should have been merged this morning. So they should be live on the Rubeus repository. And then sort of a quick overview of whether we feel that the Credential Guard solution is strong or not, and maybe some surprises at the end. And then finally a Q&A if there's time. Okay, so what exactly is Credential Guard? So Credential Guard runs on top of virtualization-based security, which basically runs on top of Hyper-V itself. So Hyper-V is split into what Microsoft call partitions. So a partition is essentially a virtual machine. Now the root partition is your main operating system. So in itself is a virtual machine as such, because it still uses the hypervisor to do some of the work within the root partition itself. And then you have child partitions, which could be another Windows VM or a Linux VM and so on and so forth. So is VBS a virtual machine? So the answer to that is yes and no. So VBS still runs within the root partition, but it does use the hypervisor to control access to the virtual trust levels that are running within the hypervisor. So currently there are two, VTL0 being the least secure, VTL1 being the secure world. But if Microsoft do decide to bring in new levels, obviously you'll have a VTL2 and 3 and so on and so forth. But there is only the 0 and 1 at the moment. And the reason I'm saying it's yes and no, it being a virtual machine, an independent virtual machine, it still shares the host or the guest if it's a child. It still shares the overall memory of that host. It's not separate. But access to that memory is controlled through the hypervisor. So the hypervisor then will determine whether anything from normal world will allow access to those pieces of memory that are in the secure world. Okay, so Credential Guard itself then is based on top of trustlets, and the one that actually handles Credential Guard itself is the LSA ISO trustlet. And the LSA ISO trustlet then will communicate with the secure kernel itself to handle any sort of cryptographic operations. And they communicate from the normal world via RPC typically. It's ALPC usually. So in LSASS, for example, when it needs to do anything for Kerberos, it'll use ALPC to communicate with LSA ISO for protecting secrets. So what type of secrets do get protected by Credential Guard? So NTLM hashes, Kerberos long-term keys, various other provider data as well. So it's not just restricted to Kerberos or NTLM. I imagine there's some cloud AP-based stuff in there as well. Not my area of research that I've gone into. I've specifically focused on how Kerberos is protected. And the type of things that are not protected by Credential Guard are actually the passwords that get entered into your user interfaces. So it's down to the responsibility of the application developers to make sure that they clear those credentials once they've been handed off to LSAI. So a good example where Microsoft didn't do a very good job of that is in their RDP client. Some of the credentials have been left in there where you can strip out with Mimikatz and various other tools. Now, Kerberos, some of the Kerberos service tickets are also not protected. So whilst the TGT, which is classed as a primary credential, is protected, service tickets themselves are not protected. Okay, so going on to the analysis and debugging and what was involved as part of this setup. So the targets we're interested in is HVI x64.exe. That's specifically for Intel. There is an AMD version of the hypervisor as well. So that's your hypervisor. And then you've got your secure kernel, which is the kernel living in VTL1. And then you've got LSA ISO, which is the trustlet, which is running in secure kernel land. LSASS itself doesn't need much of an explanation. And then you've got the DLLs that are living inside of LSASS and LSASS ISO that are involved for the Kerberos specifics of Credential Guard. Now, the good news with this is most of them do have public symbols, so they do help with analysis within applications like Ghidra or IDA, but the hypervisor doesn't. And typically, that is your starting point. So it does get a bit challenging to try and find the relevant areas of memory that you need to go after. The other issue you will come across is that there's far less blogs on sort of secure kernel research than the normal world counterpart. So sometimes you feel you might be a little bit on your own. Okay, so I have read through various blogs that said Hyper-V can be used for debugging the secure kernel within the guest, but I could never get it working. Whenever you had a Hyper-V guest and enabled kernel debugging, because you had secure boot enabled, the kernel debugging just didn't seem to work. So I then went back to VMware. So VMware itself has the capability of doing virtualization-based security. But what you have to make sure is that your host operating system that's running VMware has got, there's no VBS enabled on your host. You have to completely disable VBS on your host itself. And that enables you then to enable sort of like the virtualization instructions and passing them on through to your guest, which means the guest itself then can have virtualization-based security enabled correctly. So without that, you won't actually be able to start the VM. VMware will just complain that you've got a hypervisor enabled on your host and you're back to square one. Now, as far as Credential Guard itself, Microsoft's documentation is a little bit vague on this. Now, apparently, Credential Guard should only be available in Windows Enterprise. It's only licensed to Windows Enterprise. Now, I've installed education versions of it. On a fresh install, it seems to be enabled, and then all of a sudden you do an update, and then you get an error in the event log to say Credential Guard is not enabled or not licensed for this version of Windows. So if you do want to do it, just stick to Windows Enterprise because it will and should always be enabled in that particular operating system. Going on to, so there's two parts to the analysis. You've got your static analysis in Ghidra, which is helpful, but sometimes things can get a bit difficult then. So you might want the help of a debugger to step through some of this code to work out what it's actually doing. So one of the things that VMware has is the capability of setting up a GDB stub that basically listens for incoming GDB debug sessions. You can connect to the server with various debuggers. IDA has got an option for connecting with GDB remote servers as well as the Ghidra debugger, but I choose to stick with GDB. But unless you're using Pwn debug or something similar that sort of enriches GDB, it's painful. So the steps that we need to sort of follow to get to where we want to go. Our first step is to try and find the hypervisor itself within memory. From there, trying to find the secure kernel in memory. Once we've got the secure kernel in memory, we can then sort of use the symbol offsets from the PDB to try and figure out where sort of keys are in memory and so on. And then finally enable debugging of IUM trustlets that's running in VTL0. So Microsoft actually came up with the capability of debugging trustlets from VTL0, even though they're running in VTL1. But obviously production versions of LSASS ISO and various other trustlets, they don't have that policy enabled by default. But part of my goals for this as well is to try and automate it as much as possible. Quite often you're looking at structure offsets and things like that in Ghidra, which it's a pain in the ass. So trying to automate this with some GDB scripts as well was one of the goals, and making sure it wasn't sensitive to future updates of Windows as well. Okay, so how do we actually get secure kernel? So we start off looking for the hypervisor. We need to find the hypervisor first. And when you attach the debugger to GDB stub running within VMware, typically you will end up inside the hypervisor context, because it's the busiest part of the operating system. And one of the things that you can do is look at the IDTR register, which is the interrupt descriptor table register. And every CPU will typically have this register, and it's basically a table of function pointers that handle interrupts by the CPU. And if you're inside the hypervisor, that means that table will point to functions that exist within inside the hypervisor memory space. Now, the first interrupt in that table is typically the divide by 0 interrupt. It doesn't really matter which interrupt entry you pick. They all typically live inside the hypervisor, but just for simplicity, you pick the first entry in the interrupt descriptor table list, and then that will point to somewhere within your hypervisor. Then you can use the GDB debugger capability to just read backwards through memory until you find the PE header. And then once you've got the PE header, you know that you've got the position of the hypervisor within memory. The final part of that then is, inside the hypervisor, there's a structure called the segment called const. Now, at the offset 0 within that const section is the hyper call service table. Now, it's similar to the service table that you have in NTOS kernel, but this, of course, is for the hypervisor kernel, not NTOS. And then entry number 12 in that table will point to a function called hvvtl return. Now, Quark's lab done a really good job of sort of describing all this process, and I must have read their blog about 1,000 times before I could sort of get my head around how all of this works. So I do recommend you all to take a look at that as well. Okay, so why are we interested in hvvtl return? So this service call from the hypervisor is called when the secure kernel wants to make a transition back to VTL1. As we're interested in finding the secure kernel base address, it means the registers for the context that it's switching from are all likely to be pointing within the secure kernel address space. So things like the instruction pointer, the stack address, so on and so forth, they'll all be pointing to somewhere within the secure kernel. And it also means the active VMCS structure will contain those registers. So what exactly is the VMCS? So the VMCS is the virtual machine controlling structure, and it's part of the Intel VTX instruction set, and it's a structure that is pretty big. It's 4K in size. Now, the trouble with this structure is it's completely undocumented, and it's down to the implementer of the hypervisor on how that layout is in memory. So Microsoft's hypervisor will be different to maybe how VMware would do it versus KVM on Linux as well. So it's completely independent to whoever's implementing their hypervisor. The only part that's sort of fixed is a couple of fields at the top. But other than that, everything inside it is proprietary. So what that does mean then, offsets, structures, everything changes, and even changes in between builds, never mind operating systems of Windows. Now, when you hit your hvvtl return, which is what we were interested in the previous slide, the RCX register points to the virtual processor structure within that list. So you'll get, so there's a VMCS per virtual CPUs. You don't get it per VM as such, you get it per vCPU. But then what Microsoft done, they implemented another layer, which you get an additional VMCS per trust level that you get as well. So if you had 4 vCPUs, because you've currently got 2 trust levels within Microsoft, you actually get 8 VMCS structures. But when your HVVTL return is hit, the RCX register will point to that second in the second structure within that graphic that you see there. So there's lots of structures that you've got to sort of traverse to get to the VMCS, and even the register offsets within the structures are all sort of you need to figure out through reverse engineering. And like I said, they're fragile and change between even builds, never mind different operating system versions. So then I thought, is there a better way we can do this so to make it less fragile? So VTX, the virtual machine instructions as part of Intel and AMD, they come with an instruction called VM read. Now VM read allows you to read data from a particular VMCS structure, but it uses fixed field IDs that are documented within the the Intel documentation. So what we can potentially do at this point is once you've hit the HVVTL return breakpoint, we can actually patch in the instruction to perform a VM read. So it's only one opcode, so it just means you just need to patch in the one opcode that we're interested in actually reading from the VMCS instruction. So you patch it in what we're actually interested in retrieving. So there's a couple of examples you see in the image in the bottom right there. We're reading the guest CR3 register, and the IDTR base is the important one that we're actually looking for. And then you do a single step instruction after you've patched the instructions that you're interested in executing. And then once you get the data back out, which will be in the RAX register, you restore everything back to as it was so that you're not going to crash the operating system when you continue execution. So you're basically extracting information from the VMCS without needing to actually worry about where the offsets are within the VMCS structure. Using the same trick again, so we're going to read the guest IDTR register now, and now that should mean it will be pointing to somewhere within the secure kernel executable in memory. So we'll pick the divide by error, which is again the first entry within the list. And then we should be able to scan backwards, find the PE header, and then you'd have your secure kernel offset as well. So now we've got the hypervisor, and we also have the secure kernel, and hopefully in a way that's fully automated, right? Wrong, it broke. So somewhere on the road to 24H2, Microsoft in their infinite wisdom decided to remove the const section from the hypervisor, which meant we had no sort of accurate way of getting the address of HVVTL return, because if you remember earlier, I said that there are no symbols. So now we actually have no method of actually trying to find it as well. So then I was sort of like, what other options do we got? So we can sort of give up and die, or we'll perform an IDTR caching scan, which is just some phrase I came up with. But what it actually means is we're looking for different unique IDTR register values. Now, unless you're crazy and you've gone and decided to create a nested virtual machine within the target VM that you're debugging, there should only be 3 contexts that you'll ever switch between. So you'll have the hypervisor, the normal world, and the secure world. So in theory, there should only ever be 3 IDTR register values. So there'll be 3 just unique values for that boot of the operating system. So what you can do is you can take the NTOS kernel, the hypervisor, and the secure kernel PE files from your target, read the PE headers, and get the image checksum inside the PE header so that you know which one you've currently found within memory. And then you sort of loop around and run the debugger for a small period of time and interrupt and just check the IDTR again. Now, one of the important parts here is that you need to cache the IDTR, that's a mouthful, isn't it? The IDTR register. because the process of searching backwards for the PE header is actually quite resource intensive. So if you don't cache it, it means the amount of time you're actually spending in the debugger instead of versus running the operating system is a lot more. So by caching it, then you can quickly execute the host that you're debugging, run for 100 milliseconds, and then break again, so that you're taking a sample of another context that you've broken in. And then finally, if you do match the image checksum against the one you found in memory, you now know that you found secure kernel once again, and hopefully we're back to an automated solution, and it should be a little bit more robust and not reliant on certain Microsoft structures. Great, so now we're in a place where we've got hypervisor, and we're in a place where we got secure kernel in memory. Now we want to enable IUM debugging of the trustlets that are running inside secure kernel. So that is controlled by a section within trustlets called .t policy. But anything that's based on Microsoft that's production, the policy, which has got an ID of 2, will always be 0. So you can't, you won't be able to actually attach a debugger to LSASS from a production build. And you can't actually patch the T policy section either. It's controlled by Authenticode, but it's not only checked in VTL 0. They've actually checked it in VTL 1 as well, because Microsoft's attack model would basically say VTL 0 is actually untrusted. So they make sure they actually check it in VTL 1 as well. Now, at the same time as they removed the const section from the hypervisor, they also removed a function called skps is process debugging enabled. So previous to that, you could just patch that function. It's simple, very simple API. Just patch it so that RAX had a value of 1, which would indicate that debugging was enabled, and you're good to go. But 24H2, they removed that function altogether. It was like as if they were trying to make my job much harder. But they instead called a function called skpsp find policy. Now the trouble with this function is it's used for all the policies that are available in that section that I showed in the previous slide, which means patching it now is a lot more difficult because it covers far more policies. It's not just the debug enable policy. So what automated options did we have for this? So what we could do is we can put a breakpoint on skps find policy, and all of this is through GDB scripting engine. So you'll also get a callback to say that the breakpoint has been hit. We can read the RDX register for a value of 2, which is the policy type, and then we can write the value of 1 to the address that is held at R9 register, which is the policy value result that the caller is interested in obtaining. And then we read the return address from RSP. We can set the RIP pointer then, or the instruction pointer, to that return address that we've just read back, set RAX to 0, which just indicates success of the function, and then we increment RSP by 8 bytes to simulate that we've returned from the function. And this is identical to how hardware breakpoints in the AMSI bypass works, but we're just doing it on a different function. But the concept is exactly the same. Okay, so quick demonstration. So on the left there, you got x64 debug. I'm just going to try and attach to LSASS. And then obviously it's terminated and you can't actually attach. And now we're going to attach to the GDB server running inside of VMware. And we're going to run our script. Okay, so that's now doing the IDTR caching scan that I talked about earlier. Now, one of the issues, as I did allude to earlier, is that the secure kernel context is probably the quietest part of the operating system. Hypervisor is most likely the most likely context that you're going to land in, and NTOS kernel is sort of like the bit in the middle. But from testing, anything from sort of 15 seconds up to about 2 minutes, 2 to 3 minutes is the longest it's taken before it ends up landing within secure kernel context. So hopefully we'll be just about getting to the end of that. Okay, so we're now in the secure kernel context. So just printing out some of the secure kernel variables, and now I've enabled that automated breakpoint function for IUM debugging. Going back to our VM now. Something happened here where the alignment of the mouse had gone off from the menu. Some VMware had a spaz, but hopefully it kicks back in. There you go. So we now try and attach to LSASS. Now we can attach to it. And you can see down the bottom right as well that it's just indicating that IUM debugging has been enabled for LSASS. So what that basically means now, from VTL 0, you can now do dynamic analysis in addition to your static analysis that you may be doing through Ghidra, and it just makes it easier to fill some of those gaps that you potentially would need to fill just from the static analysis. Okay, so we're now in a position that we can do both static and dynamic analysis. So inside secure kernel, there are six keys, and they all have various purposes. Now, the ones that are involved for Credential Guard are the local keys, or the LK keys you can see there, and it's actually the LK array handle symbol that it uses for most of it. Now, the MK per boot handle is for trustlets that want to encrypt data that is just for that boot, so that it's not persistent across a reboot. The local keys are the same keys, so you get the same key every reboot. So they are for secrets that you want to make persistent. The ID keys down the bottom, they are used for, sorry, not quite at the bottom, but the just before the bottom, the ID keys are used for RSA-based cryptographic operations. I haven't dived too deeply into them, but I believe they are used as part of Kerberos fast when it's using the machine-based authentication to get a Kerberos ticket, among other RSA-based operations. But it's the local keys that are typically involved. The last one on the bottom there is the Hibernate key. That's used for encrypting the page file when the machine goes to sleep. So any pages that are from the secure kernel, they are encrypted with that Hibernate key. So the secure kernel has no actual capability of writing to disk using files. It's much simpler. So you can't read the registry, you can't write to disk. So they pass over that to the normal world, but they protect any pages from the secure kernel using that HBK handle key down the bottom. But it's the local keys that we're interested in. They're the ones that are used for protecting Credential Guard secrets, and it's through the IUM Crypto Secure Service Corp. Okay, so they are passed from the SKE loader block. So that's passed from the bootloader during sort of the secure boot process, and they are tied to both the TPM and they are sealed to the PCR state registers as well. So, for example, if you change the boot order of your device or secure boot fails in some way, the keys actually will not unseal. So it means that the Credential Guard secrets can't be obtained unless the operating system is booted up in a dependent and reliable way. Now, 24H2 seems to pass through two keys. I'm not entirely sure why there's two, but in that bottom key list there where you say the LK array handle, there's two separate keys in there, and they have an ID of 1 and 2. And then it seems the most recent key gets copied to the LK handle. So you'll see that there's a duplicate there in the array version. The key ID with number 2 is actually being duplicated into the LK key handle. From reading Alex's 2016 talk on a lot of the internals of secure kernel, my understanding is over time they do rotate as the operating system is up and running. And then any new secrets that are protected are then protected with a rotated key. But there seems to be two at least that get passed from secure bootloader. So moving on to Kerberos itself. So the graphic on the right here is sort of me trying to explain what happens after you've entered your password into your normal world login process. That essentially gets passed to LSASS. LSASS then will convert that password to NTLM and the Kerberos long-term keys, and those keys will be wrapped by secure kernel. Now, one of the things that's quite interesting here is that you can't extend anything within the secure kernel. I don't think there's any feasible way of loading kernel drivers in secure kernel. It's purely isolated. So it means the trustlets running inside VTL1 don't actually have access to those keys either. It's only the secure kernel that has access to those keys. But so it gets offloaded to the secure kernel and then eventually makes its way all the way back to normal world. And the AS rec, which would be used for getting the TGT, most of that is generated in normal land or normal world, but the pre-auth data, or if you're using certificate-based authentication, that's handed off to secure world, and then eventually makes its way back to LSA. That goes to the KDC. KDC gets the response. Basically, LSASS is acting as a man in the middle, just passing through messages between secure kernel and the KDC. The encrypted part goes back to secure world. The session key is then decrypted with the user's long-term keys, and then the session key is then wrapped inside a TGT, which makes its way back to the normal world LSASS container. And that's what you basically see when you try to dump a TGT on a Credential Guard protected host. So the value of the key is -180, but more recent versions of Rubeus actually highlight that it is a Credential Guard protected blob. So what does that blob look like? So for those that are familiar with sort of PRTs, primary refresh tokens, and how they work, there's a master key, and that is derived using a context, and that key derivation algorithm is NIST's SP800-108. So you take your master key in a context, and then that will give you a derived key. So what actually happens when the LSASS trustlet wants to encrypt some protected data, it offloads that to the secure kernel, but it generates this random context as part of that process. And then a new key will be generated for protecting that particular TGT session key, for example. Now, the green header is specific to LSASS, so that gets stripped away. And all that's in there is a small sort of wrap. As you can see, there's a wrap ASCII text there, which just identifies it as a wrapped key. I'm not quite sure what the 3 is, probably a version number, but the hex 12 value is the Kerberos encryption type. So 12 in this case, or OX12 is AES 256. So that gets stripped off, and then what you're left with is the actual blob that gets sent to the secure kernel. Now, the most important parts are the highlighted parts below. The elements that are not highlighted are just certain lengths and version numbers, that sort of thing. But the parts that are actually important to decryption are the highlighted areas. So the random context that gets generated for generating or deriving the key, that's actually included in the encrypted blob. So that's the first part that you'll see in there. And then you'll get the AES GCM. So AES GCM is the encryption method they use. You get the AES GCM tag, which is essentially the H mark, just to make sure that it has decrypted correctly. That gets included in the blob. And then you get the AES GCM auth data. Now, the auth data contains things like the trust level that this data was encrypted at, and it also includes the trustlet ID that actually encrypted it. So that basically means then that even if you manage to, let's say, compromise one of the other trustlets like NGC ISO or BioISO, or there's also one called virtual TPM, you still can't decrypt Credential Guard secrets. It's only the LSASS trustlet that can actually decrypt it. So it's pretty strong, and it means that they're even isolated from each other in terms of actually decrypting the data. And then the last blob is the encrypted key itself. So a quick sort of recap on what we've seen and gone through so far. So secure world memory is isolated from VTL0. You can't access it. You can't even access it from ring 0 or NTOS kernel within the normal world. And even a compromise of a trustlet, which is purely a Microsoft thing. You can't create your own trustlet. without actually patching secure kernel through a debugger like we've done here. So even access, let's say you've managed to compromise a trustlet, it doesn't give you much. It allows you to maybe compromise the capability of that individual trustlet's capability, but you can't really affect the features of another trustlet, and you can't get at the secure kernel keys either. Kerberos TGT session keys are the only ones that are actually protected under the Kerberos ecosystem. So, you know, it's pretty unbreakable. So as part of this research, I added a few features to Rubeus to make some red team operators' lives a little easier when it comes to Credential Guard. Rubeus already had the capability of requesting tickets via LSASS or via LSA through the TGT deleg command. Now, unfortunately, TGT deleg actually no longer works if you've got Credential Guard enabled, because the TGT is essentially wrapped within Credential Guard. You won't be able to use TGT deleg either when Credential Guard is enabled. So the code was changed slightly just to leverage that same LSA call authentication package API, so that you can now request service tickets in the context of the user that you're running Rubeus under, and that will filter through LSA and use whatever TGT that's encrypted inside Credential Guard, but you will still get a ticket back. So the key decision Rubeus makes to decide on whether it uses the existing functionality or the older functionality is based on whether you supply the ticket argument. So if you supply the ticket argument, it assumes you have a TGT. If you don't supply the ticket argument, it'll then delegate that to LSASS instead. And then by default, canonicalization is off. But if you use the OPSEC flag, which is similar to the flag for AskTGT, you'll get canonicalization on as well, which is what the default is for Windows when it makes requests to LSA. So what exactly is canonicalization then? So canonicalization is basically the normalization of a username or service name that comes back in the ticket. So if you look at the graphic on the right here, we've got Joe Public. His user logo name for the UPN of his account is just Joe at ec.lab, but his NT login is Joe.public. So if you've got canonicalization on, what you'll typically get is the NT version of his username back within the ticket. Apologies if you are at the back, it's probably a little blurry. But basically what you can see in the Rubeus output on the left, I've actually requested to authenticate with the user Joe, but the ticket I actually get back, the username within the ticket is actually Joe Public. So that's what canonicalization essentially means. It normalizes the username that you actually get back. Now, when you don't request canonicalization, it reflects the user that you actually requested in the ticket. So as you can see on the right-hand side, I requested user Joe, and Joe was the user I got back in the principal. So how does LSA-ISO know it needs to protect the ticket? So as I said earlier, service tickets are not actually protected by Credential Guard. Only primary credentials are protected, including TGTs. So that is the job of a function called curb get flags for KDC reply, and that lives inside the curb client shared DLL, which is loaded inside LSA-ISO. It also gets loaded inside LSA as well, but this one actually gets called in the context of VTL1. And all it really does is check the service name of the ticket that's come back. So if it starts with curb TGT, or the alternative SPN that the curb TGT account has is kadmin change password. If it's either of those, it will then protect the TGT or the ticket with Credential Guard. If it's not, it doesn't protect it with Credential Guard, and it will be cached as normal. So if you can see with the new features that have been added to Rubeus now, if we just request the service of curb TGT, the ticket that we get back is indeed protected by Credential Guard. So then I thought, surely that can't be the only decision they're actually making for protecting the ticket. So using a DA account, I've just added a new SPN to the curb TGT account called not curb TGT /service, and then I try to request that particular service ticket. So it's still linked to the KERB-TGT account, but I'm just using a different service principal name. And you get a ticket. It's not protected, but who really cares? You need admin to sort of add a service ticket to KERB-TGT account unless you're in an environment that's going to be in trouble. So then I thought, so what can we sort of leverage this feature from an unprivileged perspective? So my DC31 talk went into some of the service principal types that you can request. Now, a lot of this back then was based on the service type for a user principal, but both service types for user principal and a service, they're essentially the same. So what I've done now is added the functionality within Rubeus to actually request what service name you want, format hint that you want to give to the KDC. Now, the trouble you have is quite easy within Rubeus when you go in direct, because you've got direct control over the packets that are sent to KDC. But when you're proxying through LSA, which is what we need to do when we're working with Credential Guard, you're at the mercy of what the API is actually offering. And the public docs didn't really advertise a way this could be done. So again, we're back into Ghidra, stepping through code to see what capability we have in terms of controlling the hint that we want to give to the KDC for what the service type is. So I came across a function called KERB process target names. And I could see in there that he was looking at the service principal name for certain characters within the username or the service name that you were requested. So for example, if you had the @ character in there, it would switch the name hint to KERB NT Enterprise, which is number 10 from the Kerberos specification. So I thought, okay, so we're on the right track here, and it seems to be controlled by the format of the string that you provide for either the C name or the S name within your request. And then I got to this other part. So I thought, oh, that looks a bit strange. Why is there 3 ats per here? And what they're basically saying is if the service principal name starts with 3 ats, we're going to use service type 6. Now, if we go back to the RFC, we can see that 6 actually represents the X500 principal or the distinguished name. So another quick demo here, you can see I've got Credential Guard enabled on this target VM that we're doing our research on. But just to show that we are active with Credential Guard, I'm going to dump the tickets anyway. Most of them are service tickets, so no different. But then we've come across a TGT that is protected with Credential Guard. So using the new Rubeus features now that we can request the service that we're interested in, which you can see is a distinguished name, and the new service type argument, which gives the KDC the hint that we want to use X500 for the service name hint. And then we get an unprotected TGT coming back from LSA. Now, one of the issues you do have is that the format for the service name is not the format that the KDC expects. So we can use the TGT sub command to then rename it back to KERB-TGT so that the KDC sees the format that it's expecting, because that's not protected by the checksum flags within the TGT. So you can replace service names. Now I demonstrated this just to make the video easier to follow on the same host, but in theory you could take that TGT ticket and away from the host, which of course is what Credential Guard is designed to stop. And then we're going to request an LDAP service ticket with this particular TGT. Now this is using the normal Rubeus methods now. It's not being routed through LSA. And then we get an LDAP service ticket as well. So this was fixed in January 2025's Patch Tuesday. What Microsoft decided to do was just simply add further checks for the common name within the service ticket that comes back. They also check for derivatives of that as well, so it strips out spaces and anything like that. So basically, also now if you have there's a typo there, that should be CN, not DC. But if you have a common name equals KERB-TGT comma in the service name, it will now get protected by Credential Guard as well. But, you know, even if you had that within another sort of OU within LDAP that was unrelated to KubeTGT, it will still get protected by Credential Guard. But you can still bypass it, like I said earlier. If you've got write access, write SPN or generic write over KubeTGT in your environment. I have seen it once or twice. You don't see it often. Typically, write access to the KubeTGT itself doesn't really give you much, because you can't even set the password for the KubeTGT secrets, because they get randomly generated anyway, and you have to DC sync to be able to get them back. So I suppose you could argue, you know, that this is one attack vector that you could potentially use. If you do find you've got write SPN or generic write on KubeTGT, you can just write an alternative SPN to the KubeTGT account, and then you'll have a bypass for Credential Guard. So some of the references, definitely read that QuarkSlag blog thousands of times. I really recommend you have a read of it yourself. But then Alex's blog, Black Hat talk from 2016 was a massive help for all of this. But then there's definitely a few other notable mentions as well that was used as part of this research. Thanks for listening, guys.
Thank you, Ceri.